So in this lecture, I want to talk about a method for a matrix factorization method that's related to singular value decomposition in a way, but it's an alternative way to get, if you like, a decomposition of your data into a low dimensional space, specifically for when your data are non-negative like they are here. These images are essentially non-negative. Actually, the raw data are negative or positive because they've been kind of normalized by subtracting a mean, but inherently it's a grayscale. So you can think of it as being, inherently they're between 0 and 1 or 0 and some maximum value. And so you can normalize the data sensibly to have, to start at 0. So although the data matrix that we were given starts at -1, you can just add 1 to everything and it's not an unreasonable thing to do, and you get a non-negative data matrix. And when you've got a non-negative data matrix, there's a method called non-negative matrix factorization that you can use to get sometimes a more interpretable decomposition of the data. So if you remember these two eigenvectors we got out of the SVD decomposition of the 2s and the 3s in the zip code data. You'll remember I said that the first eigenvector is kind of an average of all the 2s and 3s, the average of the images, and the second one is kind of a difference, and they're a bit difficult to interpret. And you might say, well, why not? We could represent all the 2s and the 3s a different way. If we have one image that's the average of the 2s and another image that's the average of the 3s, we could just, for the 2s, just load them on the 2 image and say they look similar to that image. And all the 3s would look similar to the 3 image. And that would be a rank 2 representation of the data that would, where these eigenvectors, these basis vectors, I should call them, are more interpretable. And that's one motivation for thinking about writing things in terms of non-negative things. So you can think about it this way, that one of the reasons that this is hard to interpret is that the difference between a 2 and a 3, when you look at it, is like kind of, you're canceling things out and it's a bit hard to see things. If you make everything be non-negative, it stops that cancellation kind of process. So maybe, let me just say, what it is. So instead of writing x equals u dv transpose as we did for the singular value decomposition, or you can write this as, I'll write this just as LF transpose, because this is still an n, this was n by k, this is k by k, or I might have used r instead of k, but this is k by p. So this is k by p, and this is f here is just v, and this is n by k. So this matrix is no longer orthonormal, but it's orthogonal, and these are orthonormal stuff. So I'm just pushing the d into the u to kind of make the factorization a bit easier in terms of just 2 matrices. So if we insist that L and F are greater than 0, which means each element is bigger than 0. That's called non-negative matrix factorization. And it usually only makes sense if x is also 0. And there are different criteria you might, but the simplest criteria, not necessarily the best, but the simplest criteria is, again, we minimize the Frobenius norm subject to Lij greater than or equal to 0, I should think, and Fij greater than or equal to 0. And this was invented by Lee and Sun, this idea. Okay, so so here L is a n by k matrix and F is a k by p matrix, where k is some user specified parameter that you have to say. So maybe if we're only interested in the first 2, eigenvectors in PCA, maybe we just set k equal 2 and we get the best two-dimensional non-negative representation of x, right? If k equals 2. So it turns out that the non-negative, so in PCA or in SVD, there's no constraint, right? There's no such constraint. That here, the only constraint is orthogonality of the v's and the u's, okay? Orthonormality, right? Which is required to make it unique, but there's no such constraint here. It turns out that this problem is this non-negative problem is not solvable exactly. It tends to, you have to solve it numerically. Actually, it turns out there's an EM algorithm to do that, but we're not going to focus on exactly how to do it. Just like the SVD, we're going to assume that you've got a method for doing it, minimizing this. Although you should be aware that the method is not exact, which means, it's a numerical method that, like the EM algorithm, it optimizes this by a hill climbing approach. And if you initialize the algorithm differently, you might get a different answer. So that's a caveat to these kinds of methods. But that caveat aside, it turns out that the L's and the F's that you get are often more interpretable than the ones you get out of an SVD. As I say, this is really mostly in cases where X is non-negative. It makes sense. So let's look at the image data again. So here I apply it to the images to get the two. So now again, the idea is I want to get two eigenvectors so that every image can be kind of written as a linear combination of those two eigenvectors, but here the eigenvectors have to be non-negative and the linear combination weights have to be non-negative. And the result is that it picks out essentially kind of a canonical 2 image, that's that first one, and a canonical 3 image, that's that second one. So these are the two quotes eigenvectors. They're not eigenvectors anymore, basis vectors, let's call them. These are the two basis vectors it picks out. And then every image is loaded in a non-negative way on one or both of these images. So you can see that many of the images, here, these images are only loaded on this basis vector because they have 0 loading on this basis vector. And these are loaded only on the other one. So you see a lot of images get put on one basis vector or another, and that makes sense because one of the basis vectors kind of represents a 2 and the other kind of represents a 3. So what you'd hope is that the images that are 2s would just get represented by a loading on the 2 and nothing on the 3 and vice versa. But of course, because the data are messy, there are some images or 2s or 3s that look kind of like a hybrid. That you need, they're better represented as a combination of these two images than they are by any one. And so that's these cloud of points here. Okay, so just like the SVD separated out the 2s from the 3s pretty nicely, you can see the non-negative matrix factorization also separated out the 2s from the 3s pretty nicely. But now the basis vectors themselves are kind of more interpretable because of this fact that they're essentially, because by disallowing the non-negative, disallowing negative entries, you get more interpretable results. If you're interested in another, let me just show, this is if you do it to the 6s and the 3s instead. So you get one basis vector that's a 6, essentially a 6, and another that's a 3s, and I didn't plot the loadings, but oh, I did. There you go. So you can see that they're well separated out in the two dimensions. And this is what you do. I just did all of them, and I tried 10. I guess I was hoping to get, if I used 10 basis vectors, I would get the digits 0 to 9. That didn't happen. I increased it to 12 to see if that would help, and also because it was nice to get a plot of 3x4 plot of 12. But it still didn't quite happen, but you can see some of the digits kind of come out of this basis representation, but some are not. So it's not a foolproof kind of, these are a bit messier. You might have hoped, again, to get a basis of 1, 2, 3, 4, 5, 6, 7, and then each image would just get loaded on its, on the image that it corresponded to. But of course, the data are noisy, and so you actually get these kind of, you know, you get probably an 8 is some combination of this one plus maybe some of this one, right? So you can see that 8s are going to get split across multiple basis vectors. And actually so I was curious as to whether you get the same results when you run it 3 different times. So you get similar, you can see that these 3 lines, which are not exactly on top of one another, they're just 3 different runs of the NMF in terms of that Frobenius norm per iteration. So the x-axis is iteration number. Sorry, I should have labeled them. Y-axis is mean squared error, the Frobenius norm. So you can see it starts at a random point, it improves quickly, and then, you know, the 3 seem to get somewhat similar answers. I looked at them visually. None of them like picked out anything much better than this in terms of interpretability. So if you're interested in the in more examples of that, there's let's have a look. Oh, sorry. I believe this one here. Check I got it right. No, I won't do that now then. I believe that article there, I'll check after, but I believe that one is on the non-negative matrix factorization, and gives you some more pictures that illustrate the idea that sometimes the vectors can be more interpretable with the non-negativity assumption. So it turns out non-negativity is not the only assumption you might get. Another common assumption actually is you want to get sparsity on these things. So in other words, you're looking for factorizations like this, but with, say, the L and the F's are sparse. And that also can give more interpretable results. Think about it this way. If you can represent each image as just one basis vector rather than multiple basis vectors, that sparser representation is going to be kind of cleaner in some ways, because it means that each basis vector will correspond to the corresponding image. So you could imagine that maybe getting a sparse representation in the L's would allow us to get a more interpretable basis. It's a bit closer to clustering there, actually. If you think about it, clustering is where each point is, each image, let's say, comes from a single cluster, right? So a clustering you can also think of as matrix factorization, or kind of similar, where all the L's, you're only loaded on a single, so the basis, the F's represent the cluster means, and each image is loaded on just one cluster. And so the L's are a binary indicator for whether the image came from that cluster or not. So clustering is also represented, you can think of it as a very sparse version, a very particular version of matrix factorization. So that's the way I tend to think of these things, is that PCA is kind of a generalization of clustering, where you're writing everything, instead of writing it as a cluster plus noise, a cluster center plus noise, you're writing it as a linear combination of these eigenvectors. And the non-negative the same. Instead of writing it as a cluster, it can be a linear combination of, quotes, cluster centers, if you like, which allows you to have hybrids between clusters. And if you're interested, we'll probably talk about this again. You know, there are topic models are also a generalization of clustering that allow things to be members of more than one cluster. They also have an interpretation in terms of matrix factorization. Okay, so these are all very useful methods. I should say, I guess also there are other methods for like trying to plot things in a low dimensional space, usually 2 dimensions, such that you know, the picture preserves the similarity, that the similarity between observations is reflected in their distance apart in the 2-dimensional space. So that's, you know, that's true of this picture, right? Is that points that are sit close together in this 2-dimensional space are also more similar genetically, on average at least. So this, you can think of that as another way of what this representation is doing. It's trying it in 2 dimensions to put things that are similar nearby and things that are not similar far apart. And you can frame that problem in different ways and define different objective functions for that. And so one common way, again, that that needs a lot of tuning, but is very popular right now in genomics, is this thing called SNE, T stochastic neighborhood embedding, and there are also nonlinear versions of principal components analysis that have similar ideas. Manifold learning is another buzzword, and so the basic idea is that these, at least between of T-SNE and some of the other methods, is it tries to put together in two-dimensional space the things that are very similar to one another, and it doesn't worry so much about the things that are very different from one another. So it doesn't really matter if A and B are very different, it doesn't worry too much about how far apart they are. But if A and B are very similar, it wants them to be very close together. So it tries to preserve, so it gets a two-dimensional plot that preserves the local similarities, so that things that are very nearby to one another in the plot are very similar to one another in the original data, but they don't preserve the global structure, which PCA does try to do. And that can have advantages if, you know, if the local structure is what you're most interested in, if you're interested in clusters, basically, then T-SNE will give you a much nicer cluster-like representation of the data in 2 dimensions than PCA will. Okay, so this is just to say that there are other dimension reduction techniques that have this idea of trying to represent data in a low dimensional space such that distances are preserved.